Hello and welcome back to our machine design series. Today we are continuing our discussion of gears, spur gears specifically, by talking about meshing considerations. So when two gears are moving together, their teeth are interfacing, the driving gear is driving a driven gear, we call those two gears in mesh. And the relative motion between two gears in mesh can either be pure rolling contact or it can be some combination of rolling and sliding contact. Okay, and this is important when we're trying to think about the failure modes of gears, and we're going to talk about that more in a future video when we start talking about loading of gears. But keep in mind that when two gears are experiencing pure rolling contact, we're only experiencing those normal contact forces. When we have a combination of rolling and sliding contact, that sliding contact is going to cause shear forces to act on the surface, which can lead to surface fatigue. And if you're curious about surface fatigue, then you can go back and take a look at our video on that in the bearing section. Okay, so next let's talk about the contact ratio. And the contact ratio is simply going to be what it sounds like. It is the average number of pairs of teeth that are in contact at any given moment. So let's draw a quick picture of this so we can understand it a little bit better. Okay, so as a little bit of a review before we move on with this drawing, remember that the base circle is the circle that our circle involute is drawn from. So if you go back, and I'll even scroll up, look at the profile of a circle involute, which is how most gear teeth are shaped, is to form this circle involute shape. This circle that our yarn was wrapped around is the base circle of our gear tooth, and then the involute profile comes from this line that we're tracing as we unwrap a piece of yarn or a taut piece of string from that base circle. Okay, so that's our base circle. Our pitch circle, remember, is the theoretical circle that we use for many calculations. It intersects the pitch circle of the mating gear at a single point called the pitch point. And then we have these addendum circles drawn, and those correspond with the top side of the teeth on either gear. Now, the pressure line, the line of action of the contact force, it starts at the intersection between the base circle and the addendum circle for one gear. So that would be here. And then it goes through the pitch point and to the intersection between the base circle and the pitch circle on the other side. Okay, and remember, the angle here we just talked about in our previous video. This is our pressure angle, phi. But the thing that we want to take away from it for this video is that we want the length of this line from A to B to be able to calculate the contact ratio. So that length of line AB is the length along which a pair of teeth will be in contact. And then we need to divide that by something to get the number of teeth in contact at any given time. And since this line, AB, is tangent to the base circle, we can use the base pitch to calculate our contact ratio. So let me write all this up, and hopefully seeing it will help it make some more sense. Alright, so our contact ratio is the average number of pairs of teeth in contact. When one pair of teeth is in contact, as we move from having that pair of teeth in contact to the next pair of teeth in contact, we're going to need to have, at least for a very brief period of time, that both of those pairs of teeth are in contact at once. Otherwise, if we have instead a gap of time where there's no teeth in contact, then that can cause some dynamic forces impact between the next two teeth when they do finally make contact with one another. And so we're going to have a recommendation that you design gears with a contact ratio typically greater than 1.2. Okay, so this is, of course, as with many recommendations, there are exceptions to this rule, but this is a good guideline. And then finally, let's write out our equation for the contact ratio. It is MC equals LAB, and that LAB, again, is the length of this line, the line of action between points A and B, divided by our pitch of the base circle, our base pitch, which in our last video we found a way to relate that to the circular pitch, P, by using cosine phi, cosine of our pressure angle. Alright, so that's the contact ratio. It tells us the average number of pairs of teeth in contact at any given time. So now let's talk about another concept, the concept of interference, which occurs when tooth profiles of meshing gears are not perfect involutes, which means they're not perfect conjugates of one another. And then when contact is occurring in that non-involute portion of the gear tooth, we have interference. So that's a lot of new terminology being thrown out all at once, but let's copy our image up here and I'll try to draw what I mean. Okay, I think this is as good as we're gonna get. So here I've drawn two gear teeth which are coming into contact with one another. I've labeled those points A and B once again on the pressure line so that we can see where this contact is actually occurring is up here. We'll call this point C. And the reason for that is because these tooth profiles are not exactly conjugate. You'll notice that the base circle, which is this dotted line for both of them, the base circle does not mark the end of the gear tooth. It actually extends down below. The profile of that gear tooth continues. And same thing on the upper side. The base circle is here, but that doesn't mark the end of the tooth. It actually continues a little bit further down. And at that location, that's where we would expect to see some interference. Okay, so really this base circle, I suppose, to be completely accurate, we should move it a little bit further up around there. Right, so your interference is going to occur outside of the base circle. So let's think a little bit more about why this is. Contact is going to begin when the tip of your driven tooth, which in this case, let's say things are rotating this way, which means that this one is rotating this way. The flank of gear 2 is contacting the tip of gear tooth 3. And when that happens, it's actually before the involute portion of the driving tooth is even within range. So contact is occurring below this base circle of gear 2 and on the non-involute portion of the flank. And so the effect of this is that we start to get some wear, and the mating tooth will start to kind of dig out the material on this portion of the gear. The same thing will happen when the teeth leave contact. Contact should end, at a certain point, but it actually extends a little bit further than that. Now, we can sort of avoid this when we perform a process called undercutting. So we can cut these gear teeth so that there is more of a gap underneath the base circle, and that will help eliminate this interference. When this mating tooth would be digging out this material, there's nothing there, so we avoid that interference. The problem is that this can considerably weaken the gear tooth. So think about, all this stress that's being built up in the tooth from this contact. We're kind of bending the tooth back this way with the normal contact force that's being experienced by this tooth. And when we do that and we eliminate some of this cross-sectional area that was carrying that weight, what we're doing effectively is we're making the stress go up considerably. So undercutting is one possibility for eliminating interference, but effectively what you do is substitute one problem for another. So it is not a cure-all for this problem. All right, so one more potential issue with meshing gear teeth before we wrap up this video, and that is backlash. So backlash is simply the difference between the tooth thickness and the width of space. So if I can measure my width of space, meaning the space between gear teeth, and my tooth thickness, then I can understand how much of a gap there is when the two teeth are meshing together. Now, we need at least a small amount of backlash, or the gears will actually bind together. So if there's not enough space for the gear teeth to move relative to one another, then they'll sort of get stuck together, and that is called binding. But too much backlash can also be problematic, particularly if you are planning on using the pinion both in forward and in reverse. So when we reverse directions of one gear, this backlash, this extra space between the teeth, will get taken up by that backwards motion, and that can cause dynamic forces and impact and all kinds of high loads that could lead to additional damage to the teeth. Okay, so our backlash is this gap that exists between these two teeth. So this gap right here. And if I were to now reverse the direction of this gear, take this omega 2 and go in the opposite direction, then this backlash, that gap, would be taken up by this gear tooth moving until it contacts the other side of the geared tooth on the top side. So that movement can happen very quickly if there's nothing damping this rotation, and when it does finally hit, it can cause some damage from the impact, and that is the phenomenon of backlash that we're talking about. All right, so with that, I hope this video was helpful, and I hope that you're looking forward to the next one, where we will start talking about gear trains. So how we can use all these concepts to design gear trains that help us transfer power, torque, speed, and all the trade-offs that we have to balance when we're designing a gear train. So, thank you again, and I hope to see you in that next one.